Welcome. In this video, we will be learning about solving systems of linear equations using the Gauss-Jordan elimination. Matrices. A matrix is a table with rows and columns. A matrix is identified by the number of rows by the number of columns. A matrix is denoted by brackets. In the first example, we have a matrix that has 3 rows and 2 columns. So for us to label this matrix, it is a 3 by 2. And normally we label it at the bottom right hand corner. So for the middle example, I have 4 rows with 1 column, so this is a 4 by 1. Go ahead and pause and try number 1 and see what type of matrix number 1 is. With problem number 1, I noticed that it has 3 rows and 3 columns, so this is a 3 by 3. A square matrix is a matrix with the same number of rows as columns. Identity matrix is a square matrix where the main diagonal line are 1s and all other numbers are 0s. So for a 2 by 2 matrix, your main diagonal line would be contained 1s, all other positions are 0s. For a 3 by 3, the identity matrix, again, the main diagonal are all 1s. Everything above and below are 0s. And the same thing for a 4 by 4. Your main diagonal 1s. Everything else are 0s. Notice that we have a lower triangle. And we have an upper triangle. Creating an augmented matrix for a system of linear equations. An augmented matrix is where there are 1 extra column than row. A row would be represented by each equation, and a column would be represented by each variable and 1 additional column for the constant. So what we want to do is we want the x's to represent 1 column, the y's represent another, and your constant representing the last column. So this matrix is going to be a 2 by 3 because there are 2 equations and 2 plus 1 columns. So I'm going to lift out the numbers. I'm going to lift out the 2, the -1, and the 7 on the first row. The second row, I'm going to lift out the 1, the +4, and the -5. And sometimes you will see a vertical line right before the last column to represent the equals. Before we can write it as an augmented matrix, we have to make sure we have it in the proper form. And the proper form is the fact that the x and y must be on the same side, with constants must be on the other side. So for the middle example of 2x is equal to 5 minus 3y, and 4x is equal to 11 minus 7y, the first thing we need to do is we need to move the 3y and the 7y to the other side. So that will give me 2x plus 3y is equal to 5. 4x plus 7y is equal to 11. Once you have it in that format, you have an x column, you can have a y column, and you can have a constant column. And lifting out the numbers, I'll lift out a 2, 3, and a 5 going across on row 1, and a 4, 7, 11 for row 2. Go ahead and pause and see what you can do with try 2. Hint, if there's a variable missing, put a 0 in the matrix. So for try number 2, I do have it in the proper format in the sense that all the variables are on the left. They are in their own little columns, all constants to the right. Because this is 3 variables, I want to have an x column, a y column, and a z column, and my constant. So this is going to be a 3 by 4. So my first row is going to be 1, 1, -1, and 7. My second row is going to be 0, 3, 2, and 1. And my last row is going to be -2, -5, 0, and 6. And that's how you do an augmented matrix for a system of equations. Now we should be able to take an augmented matrix and write it back into a system. we're going to use the variables x, y, and z. So in the first problem, where I have a matrix of 1, 2, and negative 6, 4, 1, and negative 3, the first column is always going to represent my x, the second column is always going to represent my y, and the last column is always your constant. So here I have 1x plus 2y is equal to negative 6. 4x plus 1y is equal to negative 3. So go ahead and pause and see what we can do with try number 3. It is a 3 by 4 matrix, with the first row being negative 1, negative 2, 3, and 6. Second row 0, 4, 1, and 2. And the last row 2, negative 1, 0, and 9. Okay, so I'm able to translate this knowing that the first column represents my x, second column represents my y. I want to let my third column represent my z, and my constant is always my last column. Equation number 1 is negative 1x minus 2y plus 3z is equal to 6. 0x plus 4y plus 1z is equal to 2. 2x minus 1y plus 0z is equal to 9. And no, you don't have to write the 0x's or the 0z's. With try number 4, go ahead and pause, see what you can do. It is a 3 by 4 matrix again. The rows being a 1, negative 2, negative 10, and negative 6. Row 2 is 0, 1, 8, and 3. The last row is a 0, 0, 1, and negative 1 half. So be able to write it back into a system. That would give me 1x minus 2y minus 10z is equal to negative 6. 0x plus 1y plus 8z is equal to 3. And 0x plus 0y plus 1z is equal to negative 1 half. Again, the zeros are not necessary. Gaussian elimination is where the augmented matrix has the main diagonal line values of 1 and all values underneath the diagonal line of the 1 are zeros. For example, the last problem we did, the try number 4, that was a Gaussian elimination form. An automated matrix in Gaussian elimination is also called row echelon form, or REF. Now, Gauss-Jordan elimination is where the augmented matrix has an identity matrix on the left of the constant column. An example of an augmented matrix in Gauss-Jordan elimination form is 1, 0, 0, 2, 0, 1, 0, 1 half, 0, 0, 1, negative 2. An augmented matrix in Gauss-Jordan elimination is also called reduced row echelon form, also known as RREF. Rules to solve a system of linear equations using the Gauss-Jordan elimination. With Gauss-Jordan elimination, the problem is worked by columns, but the operations are done by the rows. There are 4 row equivalent operations. Operation number 1 is that any row can be switched with any other row. Rule number 2, a row can be multiplied or divided by a non-zero number. Rule 3, a row can be added to any other row. And rule 4 is actually a combination of 2 and 3, where a row can be multiplied by a non-zero number and then added to another row. The way that rule number 1 will look in terms of symbols is that row 1, double arrow row 2, and that double arrow means switch. For rule number 2, it could be a fraction times row 1, and the arrow to row 1, which means that the new answer is going to replace row 1. The same row is what you're trying to fix. Rule number 3, row 1 plus row 2, arrow row 2, which means that you're adding the 2 rows and the answer is going to be placed in row 2. And rule number 4, you can multiply a fraction to a row, then add it to another row, and that's going to be put in a new row. So after an operation has been used, the new equation will replace a previous equation. The arrow designates which row the new equation will be placed. Steps to solving the system of equation with Gauss-Jordan elimination. Step number 1. Write the system of equation into an augmented matrix. Step number 2. In the first column, by using the row operation rules, get the first row first column position to have a 1. Row operation number 2 works for this step. If a 1 is located in another row, then switch to 2 rows. Step number 3, once step 2 has been completed, get the rest of the values in column 1 to be zeros by using row operation number 4. Next, once column has 1s and zeros, then move to the second column and get the second row to be a 1. Now, get the rest of column 2 to be zeros by using row operation number 4. Continue to repeat steps 3, 4, and 5 until all columns contain just 1s and zeros. The problem is completed once the identity matrix is located on the left side of the constant column.